Mike.
Hi, Brian. I started the recording. So hello, everybody. My name is Rob Maines. I want to welcome you here to our first edition of the CHIPS Deep Dive Cafe. I'm pleased to announce that we have Carol Gugula from Antmicro with us today to talk about different open source efforts in different contexts, primarily FPGA and embedded software. He's going to be chatting about his work on scheduling in Verilator. Just give you a few minutes of introduction here to CHIPS Alliance. So I recently became the general manager of CHIPS. And I want to talk a little bit about that. Brian, if you could go to the next slide, please. Thank you. So, if we look at where industry has come, we've kind of gone from a soups to nut type of environment that we've seen with many of the large companies over time. General Electric, IBM are two examples, AT&T, where literally somebody like with GE would have a foundry to pour the metal cast for the turbines that they made and then sold out to utility companies. Similarly, IBM and AT&T, they had their own foundries. They did the design, they did the operating system that went in, that made up the computer systems that they sold. To now where we see what I call more of a supply chain management type of thing, an overseer or just-in-time type of deployment of materials as needed. Apple would be one example of this as one, NVIDIA is another, where they rely upon a partner to do the actual fabrication for them. And similarly for their EDA tools as well, to where we're now even seeing more of what I call an open collaboration type of environment, where different companies, universities are coming together to collaborate on topics of mutual interest to try to help move things forward. Next slide, please. And so what we're really looking at in terms of compute and design challenges, of course, is that cost of hardware are increasing significantly, right? There's the NRE cost of actually building it and designing it to all the way out to getting it to product and into customers' hands. And we also see that innovation is often stalled at corporate infrastructures. There's just different limitations as to what a company can do in and of itself. And we're also seeing a need for much more purpose-built architectures, specifically accelerators that may be needed for artificial intelligence, database, IoT type of things, those similar types of things. Next slide, please. So what CHIPS Alliance is really what I call creating a concentric collaborative innovation ecosystem. In other words, openness all the way from specification out to standards. And that includes such things as RTL, PDK tooling, open PHYs, that really is hoping to change the environment or the overall landscape and to allow for collaboration between different players to bring the best innovation possible forward. Next slide, please. So in sum, if we look at CHIPS, it's really built upon a number of different things. It's open architecture, specifications, implementation, tools, verification. It's a venue for collaboration. IP contribution is certainly welcome, but it's not required to join. And how much you participate is really a function of you and your company. And we have different levels of participation that are available as options for people. So with that, I want to turn this over to Carol. Oh, just one other things I want to mention is that, specifically, we are going to be starting a system Verilog work group. We're continuing to make good progress on the area. Google really is wanting to help us move that forward. And also we recently started an analog work group as well that does starting to see some different interesting aspects being covered in research areas. And our next talk will be on July 13th, and that will be by Henner Zeller on variable and UHDM. So with that, I'd like to turn it over to Carol, and thank you so much. Appreciate it.
Thanks, Rob. Not sure if my screen is still visible. If not, let me reshare that.
Yes, we see it.
Okay, great. Okay. Hi all, thanks for joining today's talk. As Rob said, my name is Carol Gugula, and I would like to tell a few words to present our, it's not mine, like Rob said that's, I'm going to talk about my work, but it's not my per se work and only mine. It's a collaborative work from quite a few people. But I would just like to present it here. I'm just a presenter. The work on implementing dynamic scheduling in Verilator. But the whole deal here is not about implementing the scheduler and updating Verilator with new functionalities. I would like to talk about it in slightly brighter context, slightly broader context of the whole ecosystem, the whole system Verilog or testing ecosystem, and that is why I added like a subtitle to my presentation, subtitle saying towards UVM support in open source tooling, which where part of it is the work on dynamic scheduling in Verilator. But let's start from a little bit of background. Let's start from who I am and why I'm here. So if you read the announcement, it said that I work for Antmicro. I'm engineering manager here, and Antmicro is a company, private company, founded in 2009. So it's quite a few years, on the market. We are a software-driven company. We basically develop software. We focus on the software side of things. Even if we work on the hardware, we approach it as a software. We always think of software in a software way. We strongly advocate for open source, and we use open source wherever we can. It's not an empty word. It's not an empty statement. It's our philosophy. We actively contribute to open source. We actively use open source tooling, and we open source project, open source software, and hardware wherever we can. We are members of leading open source initiative like Linux Foundation, Zephyr projects, Chips Alliance, Open Power, or RISC-V. We are a founding member of RISC-V International. What we are proud of is the way we work with our approach to design methodologies and workflows, which are strongly backed with open source philosophy. We focus on many different areas, from hardware through software, including tools, including FPGA and ASIC development, all that to combine to create combined ecosystem, to create complete ecosystem where we can simply solve the problems. We don't implement things because this is something to be implemented. We solve problems with whatever needs to be done to actually solve. If you are interested in what we do, you can always visit our webpage. We have a section called Technology Showcase, where you can simply see where we publish articles and blog notes about projects we do, and you can basically read about them, and most of those notes they link to repositories, and you can even see the code or just grab the project and start working with it by yourself. If you're particularly interested in open source, we recently launched an open source portal where you can find a lot of open source projects we developed or we are strongly involved in, so we can just browse through it. You will find links to public repositories, and simply find whatever you're interested in. So getting back to our main topic, why do we actually need UVM and system Verilog support in open source tooling? Why it is so important? So as you probably noticed, if you are actively following what is happening in modern software world, the world is shifting towards open source, like in every single area. It's clearly visible in areas like servers, in areas like cloud computing, in tool chains. Basically, if you look at this market, there is open source everywhere. And of course, this shift is actually right now happening in ASIC designs, in logic designs, in FPGA designs. There is more and more initiatives in this area. Of course, Chips Alliance, and we are as part of Chips Alliance, is actively working on making it happen, and making this switch possible, making the switch doable. But with new philosophies, with new like open source philosophies emerging in digital design market, a new tools, new approaches, new methodologies appear, and those methodologies allow you to do things that were not doable previously, like implement better testing, implement better verification, implement better approach for designing the logic, the chips, and whatever is there, and those new technologies, those new approaches allow us to basically proceed faster and make better solutions in the end. The problem is that we cannot really, put a line somewhere and say that we stop using the old solutions, the old things, the old designs that are already there. A lot of people spend a lot of time doing that and just switch to new methodologies. The whole deal is to create solutions that will allow the whole market to just simply reuse and seamlessly migrate from old methodologies to a new one. So basically adapt the functionalities, adapt the approaches that were there, and migrate it to new approaches, to new way of thinking, and to new way of designing things. So why actually UVM? If you look at the market, if you look at the existing ecosystem, there is a number of projects that there's a number of digital designs that were designed in a way that was available available at the time they were being designed. Yeah, so for verification, a lot of companies, a lot of designs, a lot of engineers simply used UVM because UVM was the best verification methodology available at the time. And right now, since we have a lot of tools, a lot of new approaches, a lot of open source emerging in digital design ecosystem, and some of the older designs like that were existing there are being open source. The problem is how to verify them, and there is a lot of code base that does the verification, but it base those verification technology, those verifications methodologies are based on whatever was there, and UVM was there. And that leads to a problem where we have more and more open source design, but we cannot really build them, we cannot really test them, we cannot really verify them with open source tools. We can use proprietary tools, and those are great. They do work. They, allow you to verify things. But what they are missing is a possibility to integrate with all those new and better flows, all those new and better design methodologies, all those new and awesome open source methodologies. So you cannot really, adapt something that we know from software world, like publicly available continuous integration system, publicly available test system or continuous deployment systems with UVM-based verification. So it's not that technically it's impossible, it's because proprietary tools don't allow you to do that. Don't allow you to do that because of the licensing. The licensing is not, it's not only because it's like expensive, it's mostly because the way they are licensed, it makes it impossible to actually integrate that with open source tooling. So looking at that, it's really important to actually provide the community, to provide the whole market with something that can be integrated with this new emerging ecosystem, with this new emerging part of logic design, with tools that will allow us to use the existing code base, the existing technologies, and integrate that with this new approach. So we know what's the problem. We just need to have those tools. But what is actually missing in the existing tools? What do we need to do? What do we need to add to existing tools to make it happen? And that is not an easy question. That it's quite hard to answer. And some time ago with Google, we have created something called SVTest. SVTest is a test suite for testing system Verilog compliance in various different open source tools that are open source uh, digital design related tools. This system is actually meant to answer the question, what is missing? This system is available on GitHub. You can basically go, you can Google it and just find this, the whole suite on GitHub. The suite runs number of tests spanning from simple, I would say, unit test, testing different system Verilog functionalities, up to a complex test covering functionalities like UVM or like more complex design like CPUs or SoCs. And basically, it answers the question, which tools support what. And by just looking at the dashboard that the system produces, we are kind of able to at least try to answer the question, what's currently missing in open source tooling to provide enough support for the existing systems to be used, to be validated, to be verified and tested in open source tooling. So by analyzing, excuse me, analyzing the output of the system, analyzing the dashboard and the test results, we came to the conclusion that one of the biggest blockers is we don't really have a fast and reliable simulator that is capable of running simulations that are required by UVM, by UVM methodology. But also looking at this, at the results, revealed one thing. There is a very, very good simulator on the market. There is a very good open source simulator. It's Verilator, the fastest available simulator. The only problem with that is that Verilator didn't support simulation, didn't support simulating non-synthesizable Verilog or system Verilog code. It wasn't possible to actually run that kind of a simulation in Verilator that was required by UVM library to just run verification in a way they are implemented by many different verification suites for many different designs in pure Verilator as it was once we approached the project. The biggest missing part was actually the way Verilator handled scheduling. Let me tell a few words how scheduling is done in system Verilog. So basically, system Verilog follows a scheduler called stratified. Scheduling is defined as stratified scheduler, and this is a part of system Verilog specification. So if you grab a system Verilog specification, you can read about the way the simulation should be handled, that the scheduling in simulation should be handled in very details. But to just get you a brief idea how it works, I would try to explain, briefly explain how this should be implemented, how this should work. So the whole simulation time in system Verilog simulation is divided into slots. Each slot has a so is divided into regions, and each statement in your system Verilog or Verilog code should be evaluated in certain regions. So basically, on the right side of my slide, you can see a diagram, a graph presenting how different how the scheduling works. Just one side note: this is not the complete diagram. It just presents 9 regions, and actually system Verilog defines 17 regions, and the remaining ones are related to PLI or VPI, which allows you to remotely access simulation from external tools. But that's just a side note. So basically, if you look at this diagram here, at this flow, or this scheduling flow, you see that events from certain certain regions can affect regions that were um, that were um, that were elaborated before. So if a non-blocking assignment in this in our simulation in a certain time slot activates some statement that was evaluated in active in active region, we have to go back and reevaluate everything again. So it's not something that is trivial to implement. You have to consider quite a lot of things here. Also, some of the statements in the simulation can be postponed, and basically we should not try to evaluate them in a currently considered time slot. How Verilator handled that? Verilator actually that Verilator scheduled everything statically. So basically, during the compilation, during the Verilator compilation of a model, Verilator was resolving all the scheduling up front and just putting things in a way they should be handled. The problem with that is that if you have a potential event that will force you to go back and reevaluate everything, or events that are cross-dependent between different parallel parallel sections of the code, you cannot really evaluate them with the way Verilator does it right now. Just to get me right, it's not a flow per se in Verilator. Verilator, that was a design choice just to make Verilator faster, just to make all the simulations faster. And basically, the way Verilator schedules everything right now is absolutely fine with if you want to simulate only a synthesizable part of the code. But if you want to run simulations as UVM requires, it's not enough. We kind of have to add more functionalities, add this possibility to dynamically reschedule the evaluation, reschedule the way the simulation is handled. So together with Western Digital, we decided to work on that and decided to focus on this particular problem in simulation. And together we came with an idea of implementing a dynamic scheduler in Verilator. So basically, it ended up in quite a significant change Verilator handles the simulation. So right now, every single process that can take place in your simulation, in your system Verilog simulation, is spawned as a separate thread, like a standard C++ thread. The processes communicate. The threads, spawned threads, communicate with each other with a standard C++ mechanism. I mean, motexes, signals, condition variables, and so on. So we didn't really have to re-implement this mechanism from scratch. We just used whatever was there. Also, we didn't really have to implement the scheduling mechanism for the threads, because we simply use whatever operating system gives us. The name dynamic scheduler comes from the different approach than it was before. Previously, as I said, Verilator was setting everything at a compile time, at a Verilation time. Right now, we evaluate the scheduling, the way we should process the statements in the simulated design dynamically during the runtime, during the evaluation itself. during the simulation itself. So if you look at this diagram, we have like three processes coming from system Verilog code. Processes can be I will actually tell about those processes later. So we have a processes coming from the simulation, from the simulated circuit, and we simply translate them into threads from a thread pool we allocated. So if you look at the threads on the right side, you will see how the processes and tasks from the processes are basically put into different threads, and how they can communicate with each other. In this particular example, we can see even process A communicates with process B with events. A single simulation step looks more or less like that. So basically, we come from a previous time slot, run all the processes, they evaluate all the statements that they have to, whatever is in their list. Then we perform all the non-blocking assignments, and we get back to running all the processes if necessary, if that one triggers, if any non-blocking assignment evaluation triggers a new triggers an event that has to be reevaluated again. Yes, so we can get back to something that we already evaluated. Once everything is done, we proceed to the next time slot. This way, we can actually handle all those things that require us to get back to recalculate the state of the simulated design. So with all those things implemented, what it gives us, what functionalities it enables, what is possible right now. So one of the things that are now possible and weren't previously is handling delays. So if you look at the right side, there is a code snippet, a Verilog, system Verilog code snippet that simply spawns a forever, like never-ending process, which sets a clock signal to 0, then it delays it for one time slot and sets it to 1, and again delays it for one time slot. So previously, with the scheduler the static scheduler that was in Verilator, that kind of a code wasn't really possible. You couldn't generate a clock from a simulated design. The clock has to be always provided from a C++ test bench. So basically, that's one of the features that are right now possible, handling those delays, handling those forever tasks, which is pretty cool, because right now you can have part of your design that actually generates different various clocks for your design. The next thing that the change in the scheduler enabled is event variables and spawning a few processes and communicating with events between them. So basically, in this example, you can see two different processes spawned, and basically they do ping pong between them. So the first process is actually waiting for ping, then it delays. If it receives this event, it delays the execution for one time slot, and then it sends a pong event to the other thread, and the other thread does more or less the same, but it just waits for pong. Beside this notation, beside this at and arrow notation, we also handle event.triggered notation, and also those events can be placed in a sensitivity list of different processes. So you can use those functionalities to synchronize the execution, synchronize the simulation. So, for example, you can have a process that waits for a certain signal, like it may start monitoring some kind of variables once the other part of the simulation just sends a signal that data has been sent, for example, something like that. Yeah. Otherwise, we can simply wait for that kind of a event. Besides that, we also support forks. So basically, you can spawn a bunch of parallel processes in the system that do some kind of a logic. Like in this example, it's pretty simple example. We just display a forked process and a number, but of course you can implement way more complex logic here. And on the left side you can see a possible example output of this process. Since we don't really have any delays there, and we don't have a control of, and basically the standard system specification doesn't really say which process should be spawned when and handled when. You can have like a random output of those three, depending on how they were scheduled. So you can have like this possible output where first you get a print from second process and then from the first and third. That's just depends on how they were scheduled in the system, basically. At the end, we just do join, and once all of those processes finish, we just proceed further. Besides the standard join, the one that I just presented, system Verilog specification defines also a join any and join none, and those are also supported with this implementation. So you can also spawn a bunch of fork bunch of processes and simply wait for any of them is finished, or not wait at all and just proceed with the simulation. So basically you can spawn things like watchers of certain states of the simulated design, or things like whatever comes first, whatever interface reacts first at the simulation will proceed with next thing, next step, or whatever you implemented in your verification test bench. Next really cool feature is a wait statement. So basically, with that one, you can block the execution, you can block the simulation until certain condition is met. And here in this example, we have we spawn a process, we spawn an initial process that simply delays the execution by one time step, sets some variables, then again delay, sets some other variables, and so on. And the other thread, the other process simply blocks the execution by on certain conditions. Yes, this allows you to create a simulation where you simply block and wait for certain, even quite complex condition. Like in this example, you can have the third one is not the simplest, not the most obvious one. One additional very nice feature we added during this work, maybe not strictly related to scheduling itself, but really useful in design verification and extensively used in UVM methodology, is a constraint randomization. Constraint randomization basically allows you to create a test, create a verification test bench that will try to cover as big space, as big test space as possible, without actually necessity of running very long and very extensible tests on every single possible test case. So if you provide a very good random constraints, you can possibly explore all the or neck corners of the simulation space without really going into a problem of simulating every single possible input value or checking every possible output value. The current implementation is not fully, it doesn't fully support um, every single possible constraint, because we still working on adding some kind of solvers that will allow us to integrating some kind of a solvers that will allow us to cover any possible constraint. But right now we support some basing constraints like the ones you can see on the right side in this code snippets, like just choose something from available, or choose randomly choose something from some kind of some kind of a range or something like that. So those are right now supported, and as I said, we're working on adding real solver and being able to solve any constraint that user can provide. If you're interested in running that and using that, using those new features, we created an open source, publicly available repository presenting those examples. So basically, you can find it on GitHub, and it contains like simple examples and also simulations of more complex systems. And besides, just code there, we also have a public CI that runs those simulations and presents the results. So if you want to use it, you can simply go there and check the results of the CI, or just clone the repository, follow the README, follow the documentation, and simply run it. It would be great if you do that. If you have like use cases for those, please start using that and report all the issues you find, and that will be really helpful to make the software better and make it more usable and actually something that can be integrated into various test suites and verification suites. So it all sounds great, but as you probably you may assume that it doesn't cover everything that is required to handle UVM. Otherwise, I would name my presentation. There is an open source UVM available. Just go there and grab it. But we're not there yet. There is still some work to be done. And first of all, we're still working on the stuff that I just presented. So it's already there. It is usable. You can grab it, start using it, report some issues, test it. That will be very helpful. But still, we need to make it better. We need to find the bugs. We need to optimize it. We need to make it really robust and really usable in everyday work and everyday designs, digital designs that you and we are working on a daily basis. So one of the things that are still there, still to be done, is, for example, fully implement those randomized methods and finish class support in a way that it is required by UVM by the whole verification library. The next very important thing is merging the existing code to mainline. Right now, it is all done in a fork. It's all done independently on mainline. However, we discussed that with Verilator maintainers, so it's not like nobody knows about this work, but it's still not yet in mainline. So one of the very important thing is to merge it, and since this new approach, this dynamically spawned threads, makes Verilator a little bit slower than the regular static scheduling. We don't want to force people to use these new functionalities in in every single design, in every single simulation. What we want to do, we want to give people a choice to just introduce some kind of a optional, some kind of an option that will allow users to choose if I want to go with static scheduler, which is faster and it's good enough to run all those simulations all those simulations that want where we just want to simulate a synthesizable Verilog code. But if you want to run our verification platforms, or just run those use those features that are enabled by dynamic scheduler, users will be able to um, just enable it by a switch. The very besides merging the code um, to trying to merge to upstream, we already identified some missing features that are required by UVM. They're required to run UVM simulations, and some of them are listed here in the slides. So it's like talking blocks, assertions, like full support for assertions, class parameters, unpacked strokes, and so on. So that's still missing, and that's those parts are what we know of. So we still need to work on that and then make it implement those functionalities to actually enable it for the users. Later in the timeline, we also have a plan to integrate this work with a parallel work on UHDM. UHDM is a way of transferring evaluated system Verilog designs from between parser and other tools. And the next talk in the series will be from Henner from Google, and he will actually talk about this and the effort on this front. And as I said, that's one of the goals here, one of the future goals, to just integrate, to converge all those efforts together and make the whole ecosystem more complete. And of course, the long-term goal, our holy grail here is to provide full-blown UVM support in open source tooling. So designs like the designs like OpenTitan or Swerve that may have some UVM tests with UVM verification suites will be able, and those projects will be able to run those tests publicly and openly in repositories, and of course enable a number of users, a number of external contributors to simply simply contribute to the repositories and get their new code, the new features to be verified, to be validated, and possibly merged together. Of course, it's not limited to those two projects. It basically should allow all the projects that are there to use these functionalities to simply enable community to contribute even more to different projects that are already there, that are already available. That's all from my side. Thank you for attention. And if you have any questions, we still have some time. So I will give it back to Rob, I suppose.
Thank you, Carol. Really appreciate your presentation today, and I found it extremely informative. I enjoyed it very much. So we do have a couple of questions. Let me go to the Q&A. So I think you answered this question, but I will put it forth anyway, relative to the work that you've done in dynamic scheduling, which I think is an interesting software development problem. That's my own curiosity. But the question is from Tudor, Timmy, does this mean Verilator will be slower? with dynamic scheduling?
So, like short-term answer, like if you grab the code that's already there, yes, it will. This code is slower because it spawns a bunch of additional threads, and then we have to, sync them, communicate between them, and so on. But it's not like the goal. The goal is to we decided to implement it that way because it was simply faster. We were able to just focus on implementing a stratified scheduler as the spec requires, and just leave the rest to like whatever is there, right? Whatever like scheduling itself, scheduling those threads to operating system. Right now, once we know the functionality is there, it works. The functionality is there and it works, we may focus on optimizing it and figuring out which part of the scheduling can be done statically and which have to be implemented dynamically, and in the end make it as fast as Verilator currently is.
Thank you. So the next question is from Rodrigo Melio. Apologize if I'm not pronouncing that correctly, last name correctly. With the changes, Verilator can be used as a SV simulator without the need of the C++ code. There is documentation for that, guide tutorial, or only the provided examples on the repo?
So you still need like a very, very, very little of C++ code. That's mostly because Verilator generates a class that models the simulated design. So you still need to at least main function that will instantiate this class, and that's all you need right now. And the rest can be done in a system Verilog test bench. That's true. You can generate clocks. You can generate all the rest of the inputs, all the rest of the signals in the simulation from the system Verilog code. There is a like stub of the documentation. We're still working on making it better. That's always the hardest part for every engineer. I mean, we can write like 100,000 lines of code, but when it comes to writing documentation, it's like, oh yeah, I will write it later. So that's the hardest thing here. But if you look at the examples, I think they are pretty explanatory. So if you just go there and then see maybe it will be enough for you. And if not, just feel free to ask questions, feel free to open issues, or even try to reach us. And then we'll try to guide you through that.
Thank you. The next question is from Simon Davidman. He states, interesting presentation. On slide 2, you state proprietary licensing of existing commercial tools makes it hard to build scalable, reproducible CIs, and you said it is not price, but licensing restrictions. Can you please explain this further?
I mean, the problem is that some tools require you to provide a certain like licensing servers or things like that, and you cannot really make them available publicly because possibly then anyone can access those. That's one thing, and also it's quite hard to often those licenses limit the number of runs you can have simultaneously. So for example, we can run like, let's say 10 instances of a tool. And with a CI system, you cannot really tell how many jobs you will possibly have to handle, because if you have like a public repository and public testing, you may get like one day you can have like a single pull request, and the other day you can have like 100 pull requests because people were extremely active during that day. So, and then you have a few options like try to somehow schedule the runs, or create a queue, but if there is a lot of builds, you may end up in a situation where your build will be run like in a week or something, because it may just take time. So we cannot really spawn as many instances as you want, and you just want that. You want to do that because that's the problem. And also, the first thing I said, you may need to create a special infrastructure for licensing itself, which is often not really doable in publicly available machines or publicly available continuous integration systems.
Thank you. So we have a question from Jonathan Drolet. Is there any plan for SVA support?
Haven't heard of, but that would be really interesting.
Okay. A question from Mike Thompson. How can members of the open source community contribute to this effort?
So the whole code, the whole effort is done publicly on GitHub. So I think the easiest way is to simply fork whatever is there, write your code, and open pull request. It's either you can open, if you want to contribute directly to this dynamic scheduling, you can grab this code. If you want to make Verilator better, you can fork upstream Verilator and then contribute there. Wilson is super helpful and super informative when it comes to getting new people on board and enabling them to contribute valuable code into the project.
Thank you. I was just going to ask, just a question from my own side. I was impressed with the usage of multiple processes and threading. And I was just curious, kind of related to just the last question, but how difficult would you say it is for a new person to learn the internals of Verilator and also doing development with multiple threads and processes?
Mm-hmm. So answering the first question, it's I wouldn't say it's like really hard. Verilator is a big project and extremely optimized. So the code is not always the easiest one to read. But as I said, Wilson, the original author, is super helpful in that. So if you just ask a question, you will have the answer, and it's really helpful to just get some additional information on that. And to be honest, Verilator is pretty well documented, so you can simply read the documentation, read through the code, and get there. Of course, you kind of have to understand what C++ does. And when it comes to development of multi-threaded, multi-threaded applications, that's kind of like standard problem. Like you kind of have to have some knowledge how to debug that kind of stuff, how to use sanitizers on those, and how to deal with all those kind of problems. So it's not like harder than the other things. Maybe the hard problem here is that you kind of Verilator generates C++ code then that you later build and run. So if you may have bugs in generator or bugs in generated code, probably because of generator. Yeah. So you kind of have to learn how to correlate the generated code bugs to whatever generated does. That's something that you learn during the process.
Okay, thank you. So a question from Daryl T. Garden. Do you expect that adding multi-threading to support dynamic scheduling can eventually allow for faster parallel execution?
That's an interesting question. I mean, Verilator has a functionality for running the simulations in parallel, and it's pretty good. if this new approach can make it faster, how to tell? I'm sure we have to optimize it because right now we spawn way too many threads, and just handling those makes it slower, and handling those like synchronizing the threads and then communicating between them makes it slower. So I'm pretty sure this has to be optimized. But if it will be faster than whatever currently is, if you enable parallel processing, parallel simulation later, it's really hard task because, as I said, Verilator is really fast right now, so it's hard to make it even faster.
Thank you. Question from Amy Sutton. Is there a plan to add support for system Verilog functional coverage? This is another important aspect of design verification.
Yeah, it is somewhere in the plan, but right now there is a lot of things to be added to be able to actually so we're able to actually do that later. But yeah.
Next question is from Sung Wei Huang. Thank you very much for the talk. Can you elaborate a bit more on the overhead of the dynamic scheduler and why it is slower than Verilator?
Mm-hmm. I think I kind of explained that when I was answering the previous question. So the overhead is that we spawn a bunch of threads and we have to synchronize them. So that's always overhead because you have to system scheduler has to handle them, has to give access to those threads to resources like CPU, memories, and all that stuff. Plus we have to synchronize them. So if you do like a wait statement or you just doing simple synchronization with some events, you have to synchronize two different threads. So that's the overhead.
Okay. This next question is from Daryl Teagarten again. Does this have implications for using portable stimulus standard, PSS?
That's an interesting question, and I don't think. I mean, I don't think it has. I will try to answer that maybe after the meeting. After I have to talk with the team, and it's actually I cannot answer it right now.
Okay. So two more questions. This one is from Puneet Gold. Is there a plan to support VPI, Verilog PLI in Verilator, at least partially, as much as required by UVM, or maybe fully to make all of user SV code portable?
Actually, we did add it some time ago. Standards. I mean, we started this work some time ago with also Western Digital and with Stefan Valentovitz from Fuzzy Foundation on when we were working on adding support to CocoTB, basically to enabling Verilator to be used with CocoTB, and CocoTB uses VPI to communicate with that. So some support is already there, if not like even more than we need right now.
Okay. And last question that I have here is from Aaron Kelly. How extensive is the SV randomization and constraints? Do you leverage any existing libraries similar to System C, UVM, and Crave?
Mm-hmm. So as I said in the slide, right now it's pretty basic. So right now it allows you to just do random, the very basic randomization. But we are actually right now we are looking at integrating those libraries, the Crave libraries, and then the solver that will allow us to use full-blown randomization and full-blown functionality of that one.
Very good. Thank you. So that concludes the questions that we have.
I think there is one additional.
Oh, there's one more. Sorry. Very good. Yep. Just came in. Sorry. In SV, every data, even containers, have an associated change event. Is that supported in Verilator or any plans?
So the way the scheduler works right now, it does support stratified scheduler as specified in a spec. So the answer is, I suppose, yes here.
Okay.
And the last question, should Cadence or Synopsys consult about new development of open source? Actually, we should ask Cadence or Synopsys. I don't feel I can answer this question.
I can just comment a little bit since I have experience from my professional career at different points. So I think what I would like to see is actually invitations to EDA partners. In fact, we actually have an EDA partner who is a member of CHIPS Alliance, and to work in a collaborative fashion on different applications and to invite participation of the open source community. There's what I've learned in my short time with CHIPS Alliance, but in general, is that there's a lot of smart people out there, and providing a venue for others to contribute to different complex problems, I think would be a real benefit. And I would hope that, they would, come to the table in that sense and participate with us. I think there's a real business opportunity for all participants and also for open collaboration. So anyway, so Carol, any closing comments from your side?
I would just like to thank you for this opportunity to present here today. And I hope we'll get even better presentations in the next editions.
Well, thank you, Carol, and thank you everyone for joining us today. I truly enjoyed the in-depth presentation on your work, and I found it to be very informative. So I look forward to our next event, which I mentioned will be on the 13th of July, and we will get that out there for folks to sign up for it by Hunter Zeller. So thank you again, and take care, everyone.
Thank you. Bye.
Bye-bye.